Hey guys, second to last day of stats. Today we're going to talk about normal distribution. So we refer to graphs that look like this as normal. And usually we use approximately normal because nothing is ever really perfectly normal. But what it is a distribution. I'm thinking usually like a dot plot or a histogram, a graph of some sort that is approximately bell-shaped and symmetric. So what it does is it follows the empirical rule. It's bell-shaped and symmetric. What it means is it is not skewed to the right, or not skewed to the left, or not bimodal. So think of all those other words that we've used this chapter to describe like a histogram. A normal distribution looks like so. Unimodal, bell-shaped, symmetric, whatever. We have the empirical rule here. This might be something that you've heard of before, or maybe you've seen these percentages before, 68, 95, 99.7. The empirical rule is also called the 68, 95, 99.7 rule. And what that means is that 68% of the data fall within one standard deviation of the mean. 95% within two standard deviations of the mean, and 99.5%, almost 100, within three standard deviations of the mean. We also have a vocab word percentile, and what that does is it tells what percent of the data is below that value. You have probably heard the word percentile used in an ACT or an SAT situation. When you get your scores, they most likely will also tell you your percentile, and what that means is it tells you what percent of the test takers did worse than you on the test, basically. And so we have a couple symbols I want to go over here. We've used X bar and SX here in this chapter already, and what that means is sample mean and sample standard deviation. We're also going to introduce these new symbols. These are Greek letters. This is a mu of X, and this is a sigma. And what mu of X means is the population mean, and sigma of X means population standard deviation. So what's the difference between sample and population? Population includes every single person that, for example, took the ACT. The sample mean is, let's just say that I sampled like from high school students. And that was a sample. It's a certain subset of the population. The entire population includes every single person. The sample could be like all juniors, or juniors in M408, which is your math class, or students at From High School, or students at Palatine High School, or whatever. It's just a sample of the population. So you need to get those symbols down. Make sure you understand those. Okay, so I'm going to go right into example number 1. It says that ACT scores are approximately normally distributed. What this means, you'll see this frequently in the wording of a lot of our questions for this section. Approximately normally distributed means it looks like this. It means it follows the empirical rule. It doesn't mean that it's skewed right or skewed left or anything, so you'll be seeing that a lot in case you were wondering. And it gives you a mean and a standard deviation. And that is the sigma and the mu. That's the population mean and standard deviation of all ACT scores. So it says sketch an approximate normal distribution for the ACT scores in the space below. So what that means is I'm going to start with my x-axis, and I'm going to draw my little bell shape, and I'm going to put the mean right in the middle. The mean was 18. And it says that the standard deviation is 6, and since in a normal distribution, that means we include 3 standard deviations on each side. So put 3 little tick marks over here, and put 3 little tick marks over here. And the standard deviation is 6, which means I'm going to add 6 each time to get each tick mark over here, and I'm going to subtract 6, subtract 6, subtract 6 over here, and I'm going to label the entire x-axis. So 18 plus 6 is 24. Then add 6 again and you get 30. And then our very perfect score on the ACT is 36. You can also subtract 6 going the other direction. So that's 12, 6, and 0. And this is what the x-axis looks like in a normal distribution of ACT scores with a mean of 18. I'm going to label that with my mu symbol. It's like a cursive U. And then the standard deviation, each increment is adding sigma this direction, and each increment this way is subtracting sigma. So I'm using those symbols just so you can get used to them. And what I want you to keep in mind is that 68% of the data falls within one standard deviation of the mean. So 68% of the people that took the ACT test, their score is between 12 and 24. And then our 95 is within 2 standard deviations. So that goes out to here, and to here. That means 95% of all the people that took the ACT fall within a score of 6 and 30. That's a pretty broad range. And then the last one, this is where the empirical rule comes in. 99.7% of all test takers fall here. And in this case, for the ACT, I'm pretty sure you can't get a negative score, and you definitely can't get a score over 36. So this rounds to 100. But this is the approximate percentages that fall into each category. So just keep that in mind. In this case, for the ACT, we might as well consider this 100. But in other distributions where there might be one person who gets one score like a little bit higher than whatever this is, in the ACT, again, it doesn't make sense. That's why this isn't exactly 100, is because there could be an outlier in either direction for most normal distributions. Okay, so the only other thing that I want to talk about regarding labeling this graph is that if this is 68 in here, can you figure out what each of these increments is? If there's 68% from 12 to 24, I think you can divide that number in half and tell me what percent is here and what percent is here. 68 divided by 2 is 34 and 34. I'm going to do this as decimals because they are percentages after all. Okay, so the next thing, how do I figure out what this increment is and this increment is? So what I'm doing is I'm taking my 95 and I'm subtracting the 68 and then dividing that number by 2 because part of it is going to go in this area and part of it is going to go in this area. When you do 95 divided by or minus 68 and then divide it by 2, you get 13.5%. So 13.5% is here and 13.5% is here. Mathematically, you guys can figure this out. You don't need to memorize this. Take your 95 minus your 68 and divide it by 2. It gives you 13.5% each part. Next, I'm going to label this increment and this increment. When you do 99.7 minus 95 and then divide that by 2 to get this increment and this increment, you get 2.35%. So 0.0235. 0.0235. And then last thing is you take the 100% of the entire bell curve and subtract 99.7 and divide that by 2, and that gives you the very, very tiny percentage that goes on each of these tails, 0.0015, which is 0.15%. 0.0015. Okay, so it's going to be helpful maybe so that it's just faster for you to label the graph to memorize these numbers, but if you forget, you remember the 68, 95, 99.7, you can mathematically compute them. And so why did we do this? Why are we labeling this score? Because now we can answer all of these questions down here. Find the percentage of scores that are between 18 and 30. So what I'm doing is looking up at 18 and 30, and it looks like 34% plus 13.5% is what I'm going to add up for that answer. So 0.34 plus 0.135, that equals 47.5%. That means 47.5% of all people that took the ACT got scores between 18 and 30. So that's why it's useful for you to label these tick marks with all the percentages coming from the empirical rule so that you can answer questions like this. What about the next one? Between 6 and 24. So 6 is here, 24 is here, so I'm adding up 135, 34, and 34. That gives me 81.5%. Next one, greater than 12. So 12 is here. That means I'm adding up all of these decimals here, all of these ones. So I have my 68 here in the middle, plus 13.5, plus 2.35, plus 0.15. So I wrote that work in here. Remember, if it's 12 or greater, then you can literally draw a line at 12 and like highlight all of these to the right. So 34, 34, 13.5, 2.35, and 0.0015. This is what we're adding up, and that gives us our percent of 84. You guys, sometimes it's faster to do 100% or 1 minus this, minus this, minus this. So keep that in mind. You don't always have to add all of these numbers up. You could have subtracted the ones that aren't included. Either way, you get 84%. The next question says 68% of the scores are between. Well, I know that 68 falls right in the middle. That's between 12 and 24. The next one, 84% of the scores are lower than. This is a little bit harder. What I have to do is figure out which ones I have to add up. So start here and add this 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 and keep adding until you get 84. And so I just kept adding numbers until they added up to 84 and I got to the ACT score of 24. So until you get to here, add up all of these values and that equals 84. Another way of writing that is 16%. That's the complement or the opposite of 84 here. So subtracting from 100%, 16% of the scores are higher than 24. So if you draw your line here, this side equals 16%. The next one is 13.5. I recognize that number. I have it filled in somewhere up there on my bell curve. Two places actually are between 24 and, so here's 24. There's my 13.5%. The cutoff for that 13.5 is 30. Okay, if 500 students at the school took the ACT, how many of them would you expect to score above 24? So my percentage of students here above 24 is 16. That happens to be the same answer that I wrote right here. So I need to do 16%. That's the percentage of students in the entire ACT that scored above 24. So I need to take my 16% and multiply it by the 500 students at Fremd. And that gives you 80 students. So about 80 students at Fremd, I would expect to get above 24. Actually, you guys, that is probably false because typically Fremd High School does way better than the national average on the ACT. Good for you guys. So considering that this is Fremd, I would expect that number to be bigger. But that's okay. Mathematically, this is how we make an estimate. If 2,400 students in the whole district took the ACT, how many would you expect to score between 12 and 30? So my percentage between 12 and 30 is my 68% plus the 13.5. So it's these three percentages being added up. And that equals 81.5%. So adding these three between 12 and 30, that's 81.5. So 0.815 times 24 hundo equals 1956 students. So that's how we're going to use our bell curve, our normal distributions to answer a bunch of questions. You just always refer back up to the graph. So yeah, it might take you a few minutes to label everything, get your x-axis, label all these percentages in here. You know what to do with the mean and the standard deviation. That's how you get your x values down here. That's the strategy for these, and then just look up to the graph in order to answer the questions. There is one more question on the back side that I want to just remind you about. Letter I, it still goes with the ACT scores. It asks for what is the variance. And so remember, the variance is the standard deviation squared. And we were given the standard deviation of ACT scores. So the standard deviation of the ACT scores, that was each tick mark on the x-axis, is 6. And so when I square that number, I get 36 is the variance. So that was our lesson last time. Remember the difference of variance and standard deviation. You just square root the variance to get the standard deviation. So if you're given the standard deviation, you can also calculate what the variance is. This is an additional example that we will go over in class tomorrow, but you got all the notes down. That is how we use normal distributions and percentiles. So bring your questions to class, you guys. Thanks for watching and have a great rest of your night.